So what we're going to go over next is the smallest possible degree, and we'll talk about it as we go through. Okay, so smallest possible degree is going to be the smallest degree that a polynomial can potentially be. And the reason we say smallest possible degree is because when you're just looking at the graph, you don't know whether or not this is a 2, a 4, a 6, an 8, or so on, but you know 100% that the minimum it could be is a 2, okay? So that's where the smallest possible degree comes from. So let's look at this. Draw these, okay? Y equals x plus 1, y equals x plus 2 times x minus 1, and y equals x plus 1 times x plus 3 times x minus 4. So take a minute, pause the video, okay? Play the video once you have them graphed, and what we're going to be writing down is what is the degree of each of these and how many turning points does each graph have. So the degree of y equals x plus 1 is 1, and how many times does it turn, meaning how many times does this graph change direction? It doesn't change direction at all, okay? The next, what is the degree of number 2? The degree of number 2 is 2, and how many times does it change direction? Well, if I have one root, right, if I have 2 roots, I need to turn once so that I can get to that next root. It has 1 turning point. Now, the degree of the third problem is 3, okay? If I was in standard form, it would be x to the third. And the degree, largest exponent, 3. How many times did I change direction? Well, to get from here to here, I had to change direction once. From here to here, I had to change twice. So the number of turning points this one has is 2. So, do you notice what the degree is and how you can compare it to the number of turning points, okay? So the smallest possible degree, because what we don't know if I didn't have the equation, I wouldn't know if that had something to do with x to the fourth or x to the second. So to find your smallest possible degree, okay, you do number of turning points, and then you add 1, okay? Now the one special case is going to be, you're going to have a special case if you have this on your graph, okay? If you have a level, okay, if you have a level, so let's say, in this graph, you turned here, you would count that as 1 turning point. You turned here, you'd count that as 1 turning point. But if you level, you count that as 2 turning points. Okay? So the smallest possible degree of a function, of a polynomial function, is going to be the number of turning points plus 1. Because if you have 1 turning point, that means you must have came back up and hit another, which means you now have 2. Okay? So know that to find the smallest possible degree, you have to get the number of turning points and then add 1. Okay, so I have 3 examples of 3 polynomial functions, and what we're going to do is we're going to state what the smallest possible degree for each is. Now, if you notice, these are different than any of the graphs that you previously graphed, okay? You didn't have any changes in direction outside of occurring on the x-axis. That has something to do with imaginary solutions or imaginary roots, which we'll get into after we do the smallest possible degree here. So what is the smallest possible degree for each of these polynomial functions? So we can't say what the actual degree is, but we can say what the smallest possible degree is. So it goes by the number of turning points. So we have to calculate the number of turning points in each of these graphs. So once, twice, 3 times. So remember, the smallest possible degree is the turning points plus 1. So the smallest possible degree is 4, which makes sense because look, both end behaviors are going in the same direction. So what we don't know, though, is this actually a 4th degree, a 6th degree, an 8th degree, a 10th degree? We don't know that. But we know that the smallest possible degree it could be is 4. And it definitely can't be an odd degree. The next, be very careful here, okay? This throws people off. It's turning points plus 1. That's a turning point. Even, it doesn't matter that it happened on an x-intercept. That's a turning point, that's a turning point, that's a turning point. 3 plus 1 puts us at 4. Smallest possible degree is 4. Next one. 1, 2, 3, 4. So the smallest possible degree is turning points plus 1, 5. So smallest possible degree here is 5. Look, end behavior is going opposite direction. So this could be 5, 7, 9. We know it's not anything even, and we know that it has to be at least 5 because it turns 4 times, okay? So those changes in direction are what's making you increase your degree. Okay, so the next thing we're going to talk about are these little squiggles in the graph, okay? That's because you must have imaginary solutions happening. Now, we talked about something with the fundamental theorem of algebra, okay? The total, remember, if you have degree n, okay, if you have a degree n, then, if your polynomial is degree n, then your polynomial, or then you have n solutions, right? That translates to roots. So if f of x has degree n, then there are n total roots. Now you have to include multiplicity here. Now, the total number of roots are made up of real roots and imaginary roots. So the total number of roots are real roots plus imaginary roots. So you can look at a graph, okay, and determine the number of, based on whatever you're saying the smallest possible degree is, you can determine the number of real roots it has and the number of imaginary roots a function has. So that's what we're going to get into next, okay, is the real roots. So what we're going to do now is, by looking at the graph, okay, we're going to see what the smallest possible degree is. And now whatever the degree is, okay, whatever the smallest possible degree is, we can determine the number of real roots and the number of imaginary roots there are. Okay, so remember, smallest possible degree is going to come from turning points plus 1. So this has 2 turning points. So the smallest possible degree here is 3. So now, what you can find on a graph are where the real roots are, but you can't find on a graph, you can't pinpoint the imaginary roots in particular. But remember, real roots are going to be your x-intercepts, okay? Your real roots are the values, remember, your imaginary, your real roots are what are the values of x when the output is 0? Well, your real roots are going to be the values of x when the output is 0. So those are your x-intercepts. So the first thing, if we're going to get our imaginary roots, it's really a process of elimination. We know that the number, when we add these two together, has to equal the degree, right? So how many real roots does this have? Okay, this has 1 real root. This is a single root. So this has 1 real root. Now, remember, the real roots plus the imaginary roots, okay, plus the imaginary roots equal the total number of roots. And remember that if the degree is n, then there has to be n total roots. So if you have 1 real root and your degree is 3, then you have to have 2 imaginary roots. Okay? Remember, imaginary roots come in pairs or they don't come at all. You can never have an odd number of imaginary roots. That was that complex conjugate theorem. So the second one, okay, let's get the smallest possible degree. 1 turn, 2 turns, 3 turns. So 3 plus 1, so the smallest possible degree here is 4. Now let's see how many real roots, okay? So you look for the x-intercepts. And you have to include the multiplicity of each. So if I went straight through here, that counts as 1. I went straight through here, that counts as another 1. So I had 2 real roots. So remember, when you add these up, you should get the smallest possible degree. So if the degree is 4, and 2 of them are real, that means 2 of them are imaginary. Okay? And let's do one more. The last one Okay, so smallest possible degree, turning points plus 1. 1 turning point, 2 turning points, 3 turning points. 3 plus 1 puts us at 4. Now the total number of real roots. Okay, how many times does it hit the x-axis? 1. But this does not count as one real root because this is not a single. This counts as 2 because this is a double. So remember, total number of real roots, you have to include multiplicity, not just how many unique x-intercepts are there. How many intercepts are there altogether, including multiplicity? So this is one x-intercept, but multiplicity 2. So this counts as 2 real roots. And so now, if the degree is 4 and 2 of them are real, then 2 of them must be imaginary. Okay, why don't we practice one more of these, and then that is it for being able to look at a graph and determine this information. Okay, so why don't we do this kind of problem. Okay, so here it is. What's the smallest possible degree? 1 turn, 2 turns, 3 turns, 4 turns. 4 plus 1 is 5. Now the number of real roots. I have 2 unique, but that counts as 2. That counts as 1, it's a single. So altogether I have a total of 3 real roots. Remember, real plus imaginary equals your degree. If 3 of them are real, then 2 of them are imaginary. Okay, the reason I shouldn't say the reason, you're getting your imaginary roots by process of elimination, okay? If you take the real roots and you add it with the imaginary roots, you get the degree, okay? So the degree minus the real roots is what's telling you how many imaginary roots you have.